Hello there, and welcome to Physiology is Fun. Today what I'm going to do, and just remember, physiology is fun. So what we're going to do today is we're going to look at what we call the nerve action potential, resting membranes, and how they relate to the nerves. I'm actually doing it working on a chalkboard, which is something that you might not remember, but we'll see how it goes and see how clear everything comes up as I ride along. So really what we're looking at today is, here we've got a nerve. Let's put in some dendrites and the axon running down all the way here to the axon terminal. So you can see what we have: dendrite, cell body, axon hillock, nerve axon, and then here's the axon terminal. So what we'll be talking about today, or what I'd like to talk about, is just conceptually looking at what's going on with regards to this nerve and how we process information, from information coming in to information going out. Associated with this, I'll also later on put up some recordings which go through point by point what's going on at each stage. So let's first look at how we get information into the nerve. Alright, as you can see, it's a really horrible diagram, but that's okay. So really what happens is inputs come in to various points on the dendrite of the nerve, or they can come in and have an effect on the nerve cell body, as we can see here. Now what they can do is they can have both either an excitatory or an inhibitory effect when they release their transmitter onto the dendrite on the nerve cell body. So what does this mean? Well, we know from what we've looked at is that you can have either an excitatory postsynaptic potential or an inhibitory postsynaptic potential. And what happens there is that when you excite the dendrite or the nerve cell body, your membrane potential in that area will rise before coming back down again. If we're looking at an inhibitory, so this is an excitatory postsynaptic potential, with an inhibitory postsynaptic potential, what happens is we get a decrease, not surprisingly, in the membrane potential as shown here. Alright, I'm just going to rub that out. But what we can see is this can happen all over the nerve cell body. Now, if our inputs are going to have an effect and produce a response, what they need to do is they need to produce an action potential here. Now we know that for an action potential to occur, and here we have millivolts again, we know we have to go from rest up to a certain point, or a certain potential that is known as threshold. We have to reach the threshold voltage, which means we have to depolarize up from rest up to this threshold. And at that point we know that we're now going to open up all these voltage dependent sodium channels at the axon hillock, and we're going to get an action potential. But hey, we're not there yet, because what we actually have to do is we have to reach threshold. So we have to do this. And where does this have to happen? This has to happen up here at the axon hillock. So how do these guys here, how do these inputs produce an increase here? That's the important thing. How do they depolarize the axon hillock enough in order for you to get to threshold and produce an action potential? Now the thing to think of here is this is a very simplistic diagram. Really there are hundreds, if not thousands, of inputs coming in to the cell. At the dendrite, synapsing on, nerve cell body and the dendrite, all having different effects. So let's just take one. Let's look at this input here, this synapse here, and look at what happens. We know that we're saying that this synapse here is releasing a transmitter that is producing an EPSP, okay, an excitatory postsynaptic potential, an EPSP. So when we look at what that looks like, and I might use a better colour than that, alright, so let's just draw up here. So we know that it's producing this sort of excitatory postsynaptic potential, and we've seen all that before. But the thing is, you have to remember that the x-axis here is time, and that's telling us the change that's occurring here. We're not interested in that. What we're interested in is what this effect is having down here at the axon hillock. So now what we have to really look like, or look and see, is we have to see what happens to the change in potential that happens over D. And when we talk about D, what is that? That's the distance the impulse has to travel from here, or the excitation has to travel to go from here to here. So we know when we stimulate here, we're going to see a voltage of a certain amount, but then as we move away from this position, we're going to see a gradual decrease in the voltage change, or the potential difference change produced by this, because as it moves along the membrane towards the axon hillock, it's going to dissipate, and so therefore the ultimate charge that you get, or the ultimate change in voltage that's going to be produced, is going to decrease. So as it moves further and further along, it gets slowly less and less, and we can see that. So really what is of interest to us is not this value here, which correlates to here. It's the value at this point here, which is our axon hillock, this point here. And what we're interested in is how much voltage change, or how much potential change, occurs here. So let's quickly have a look. Here is the axon hillock. We're getting input from this, and let's say this change is very small, just moves it by this much. So therefore, if we get this one input from here, one grade of excitatory postsynaptic potential produced here, it will produce a minimal change at the axon hillock. It definitely won't reach threshold, and we definitely won't see a response. So what do we do? How do we get an action potential? Well, of course, we've got all these other inputs coming in. Now, let us assume that these inputs are excitatory. So we're going to have input from here, and input from here, here, and so on. All these different places we're going to have inputs, and they are all going to travel along, showing this same profile from their point of where they actually respond, or cause the dendrite to respond, or where they release their neurotransmitter, here, to the axon hillock. Now, of course, the value of D is going to be different depending upon how far away from the axon hillock this initial stimulation is. So therefore, you're going to have different degrees of changes caused by these excitatory responses. So therefore, what will happen then is, if you wish to stimulate this nerve, what you need is you need enough inputs at the right time in order for them to all to sum up and reach threshold. Now, this may take 50, 100, 1,000 such minuscule changes in membrane potential produced by these tens, hundreds, thousands of inputs in order for you to reach threshold here at the axon hillock. Once you reach threshold at the axon hillock, then you get the production of an action potential at this point. Why do you get a production of an action potential at this point? What is different about the axon hillock compared to the rest of this area of the nerve? This area here doesn't have voltage-dependent sodium channels. This area does. And it's only in areas where you have voltage-dependent sodium channels that you're going to see the production of an action potential. So, what have we looked at so far? We've looked at the fact that in order to produce an action potential in a nerve, you need to have enough graded potential changes produced by these inputs all over the dendrites that have to travel along the membrane of the nerve to the axon hillock, where they then all sum up together, and if they're great enough, they'll reach threshold and thus produce an action potential. So really, in summary, and I think that's enough so far for today, is that if you need to know, or if you want to know, this is how we produce an action potential in a nerve cell. I hope that by looking at this, you have a bit of a better understanding.